Okay, so here's where we were last time. We were setting up a context, right? Kind of a framework in which to play around with some ideas. Let me just remind you real quick. This framework that we're setting up, this bunch of arbitrary conventions of, what do we mean by an orientation? Arbitrary, right? What are the kinds of objects that we'll be looking at? What kinds of evaluations? What kinds of integrals? Vector line integrals, not scalar line integrals. Why? Where are all these conventions coming from? They're all coming from the same place. That if you take a more sophisticated point of view on all of this stuff, you can state and prove this tremendous theorem, this generalized Stokes' theorem. That's crazy powerful, right? All of the big theorems that we're going to talk about in Chapter 6 here are special cases of this big theorem. The fundamental theorem of calculus, this great, big, huge, powerful, historically important computational tool, is the most trivial special case of the generalized Stokes' theorem. Right? So anyway, this great big theorem, and too sophisticated to talk about, but if you take all those ideas that lead to this great big huge theorem and kind of boil it down to what does it look like? What are its shadows in all these various accessible contexts, like on the real number line, or in three-dimensional space on surfaces, this kind of thing. If you just look at what does it say in these contexts, it's all of these conventions that we're talking about here, right? So I'm not going to be able to justify these conventions, but these conventions are all highly, very well motivated, and again, sadly, I just can't show you that. Okay, so on with the continuation of more seemingly arbitrary conventions that, again, I promise are coming from a really good place. Okay, so let's talk about boundaries. What do we mean when we talk about the boundary, for example, of an interval? Okay. Well, there's temptation to say the boundary of the interval is 2 points, right? It's that point and that point. End of story. Well, we now have this idea of orientations on intervals. Right? It could be positively or negatively oriented. And we also have this idea of orientations on points. So what we need to do is extend the idea of boundary to keep in mind, what about orientations? And so the idea is like this. If your interval is a positively oriented, by the way, so we're going to assume we have a positively oriented interval to start with, then boundary means still these 2 points, right? The starting point and the ending point, right? But with orientations assigned as follows. The starting point is oriented negatively. Arbitrary convention. This is what makes everything dovetail and fit together and wonderful theorems come out. Okay? We're going to see how in a few minutes. And ending point, right endpoint, you might say, oriented positively. So that's the convention. It seems a little weird, seems a little surprising. Why a negative? It's going to turn out to be important. Okay, so conventions. We have a bunch of contexts in which we have to write down what is the convention for orientation. For a curve in space, 2 or 3 dimensions, whatever. Boundary, naturally you would think of the word boundary as meaning, the start point and the end point. Okay, sure, fine, fair enough. But if it is an oriented curve, now here's what orientations look like on curves. They're not plus or minus. Curves in R2 or curves in R3. Orientations look geometric, right? So suppose this is the orientation, then what are the resulting conventions on orientations on the starting point and the ending point? And the answer is the starting point is oriented negatively and the ending point is oriented positively. Arbitrary convention, right? But this is what's going to make everything fit together. Okay. All right, so y'all just have to know what these conventions are and make sure to subscribe to these conventions. Okay, proceeding along. What if we have a 2-dimensional region? And now I've deliberately drawn a kind of a weird 2-dimensional region here that's kind of it's got holes in it. Right, so my two-dimensional region here is what I have highlighted in orange here. And we can talk about the boundary. Fine, the boundary of this two-dimensional region is 3 curves. And again, you can see the 3 curves right there. And again, the temptation is to stop right there. But if this is an oriented two-dimensional region, and let's start by assuming that this is a positively oriented two-dimensional region, right? Then what is the corresponding orientation on those boundary curves? Now, again, arbitrary convention. Here's the rule, though. A lot of people will tell this a little bit wrong. The rule is not counterclockwise. A lot of people are going to tell you it's counterclockwise. That's not right. It's counterclockwise if you're going around the outside boundary, but it's not for the inside boundary pieces. On the inside boundary pieces, it's actually clockwise. And so this is that's what the boundaries are. Boundary orientations are in these cases. So the single unifying rule, it's not about clockwise or counterclockwise. What I want you all to think of it as is as follows. If you are at some point on one of the boundary curves, the correct direction to go is the direction that if you were walking in that direction, the region whose boundary you're talking about would be on your left. That's the rule. Right, so you could imagine if this is you, right, you're going that way, notice the region is on your left. And notice that has you going, in fact, counterclockwise around that outside edge. But further notice that, but if you were on one of the inside pieces of boundary, moving so that the region is on your left has you going that way, which is clockwise. Everybody see what's going on there? Okay, so it's very important that it be the way that I'm stating it, and you cannot just say I'm always going to go counterclockwise. It's wrong. Things will not dovetail if you always go counterclockwise, right? It's just not going to work out. Okay. By the way, again, I'm talking about this is for a positively oriented region. We get this rule. Everything flips if you have a negatively oriented region that you're talking about, right? And again, I hope this is no surprise, but you change the orientation of the thing you're taking the boundary of. Change the orientation of the boundary. Okay. All right. Okay. Next one. Again, sometimes misunderstood. Suppose you have a solid. Let's see here. Yeah. Okay. So a solid. Now, I am deliberately drawing, again, a non-typical solid. I'm drawing a solid here that's kind of hollow. Okay, see, it's got that chunk missing in the middle of it. So maybe this is like a racket ball or something, right? So it's got thickness to it. I mean, it's substantial thickness. It's not a balloon. It's got some substantial thickness, but it is hollow on the inside. All right, so boundary. Here's the outside part of the boundary, but there's also, don't forget, this inside part of the boundary. Now, again, not thinking about the inside part of the boundary, a lot of people will tell you that the rule is that orientations for a positively oriented solid in a space, that the orientation on the boundary goes outward, and that, again, not correct. It is better stated, correctly stated, as given a point on the boundary, move in the direction that is away from the solid. Away from the solid. Notice if you're on the inside boundary, away from the solid is not outward. If you're going to call that either inward or outward, if anything, it's inward. Right? Okay, so away from the solid is the convention. And be careful about those inside surfaces. How are we doing? Is everybody on board so far, these conventions? Okay. Make sure to know these, right? I mean, it's important to know what these rules are. Okay. All right, now here comes the last one. This last one is tough to talk about. But suppose you have a surface in space. And now, again, I've deliberately drawn a weird surface. If you take a nice, easy surface like a plane, it's a lot easier to talk about. But I want to make a general talk here. So it's this is a tough one. And here's the rule. And here's your surface. Now keep in mind it's an oriented surface. I'm going to define the orientation on this surface by a normal vector. Keep in mind the normal vector is everywhere on the domain. Right? So there's an orientation on that surface. Oriented surface. Let's talk about the boundary. Okay, no problem. The boundary is going to be a piece of curve. It might be a bunch of pieces of curve. Right? So for example, here, you can see the boundary consists of, this kind of outer edge of curve, but then there's also that piece of curve and that piece of curve. Whichever one you happen to be talking about. Look at that little piece of boundary. Several different ways to define the orientation on it. I'm going to show you the one that I think is the most useful. Which I guess subjective, right? Different people, different opinions. Here's the way I think is the most convenient, most usable. And that is, it's going to use your right hand, human right hand. Pick a normal vector that is near the boundary. Now, very importantly, not on the boundary, near the boundary. Use your right hand, point your thumb in the direction of the normal vector on that surface, right? So keep in mind, there's an oriented surface. You want to talk about the boundary of a surface, it better be an oriented surface, so you've got an orientation, you've got a normal vector. Thumb in that direction. Look at your fingers. Your fingers want to curl around a certain way. Right? So, for example, what I have drawn here, my fingers want to curl around that way. Okay, let me do that with the pencil. Look better. Pencil. Right? So that's what I'm going to call a swirl. So a normal vector on the surface will define a swirl on that surface. That's what direction do hurricanes rotate, or whatever you want, however you want to think about it. Okay? That swirl on the surface will sideswipe up against the boundary in the correct direction. That's the rule. Now, there's a different way that you could think about this. Some people prefer. I don't. But for your consideration, you could think, okay, look at that normal vector. Think of that normal vector. Keep in mind, vectors have a head and a tail. Think of this vector as representing a person, and whose head is where the head of that vector is, right? And whose feet are where the tail of the vector is. And imagine that person walking around. Well, that person should walk in the direction along the boundary so that the surface is on that person's left. And it's kind of familiar. It reminds us of that other convention, and that makes it satisfying in a way. The problem with this rule is, or this point of view on this rule, is that if you imagine a complicated scenario, where's my thing here? There we go. Imagine a complicated scenario like this one, and it's super confusing. Right? If you imagine yourself being, okay, let's see here, in this general vicinity, okay, all right, well, here's me, and I'm upside down, right? Because look at the normal vectors. The normal vectors are all like that. Right, so at this point, I am upside down. Which way should I walk along this curve so that the surface is on my left as I walk upside down? Again, there's my head, there's my feet, and you're going to go crazy. It's just super confusing, right? You'll find yourself on the exam kind of like, okay, all right, so turning your head upside, it's silly, right? So, on the other hand, no pun intended, think about how you do this with the right hand rule. It's very easy to just turn your right hand so that the thumb is pointing down. And it's very easy to just look at your fingers and say, well, okay, my fingers are swirling like that. And that swirl sideswipes up against the boundary curve that way. And there's just nothing to it. Everybody on board? So I strongly encourage you to use the right hand rule and forget about I'm going to pretend that I'm the normal vector and I'm walking along there. I think that's a formula for catastrophe. Okay. Yeah.
So then if you're like walking in the center, like between the hole and the side of the thing, like where would you go for that?
Say the question one more time. So I'm over here now?
Yeah.
Okay. And you want to take the walking point of view?
Sure.
Okay. And which piece of curve are we trying to find the orientation on? The inside piece of curve here or this outside piece of curve?
Can you not take it from the center of it? Like
Well, no, so what we're trying to figure out how to do is to find the orientation on the boundary curve. So the boundary curve has this chunk and it has that chunk. Right? We already know the orientation on the surface. On the surface itself, right, the orientation is given. It's that. I don't need to figure out the orientation on the surface. Does that make sense? Yeah. So the question that we need to figure out, though, is given that orientation on the surface, what's the orientation on the boundary curve? And, we just need to break that down into separate questions, one for each chunk of boundary curve. So, let me just kind of proceed with this. So let's look at that piece of boundary curve. Right? So you could ask the question of, okay, again, here's me, turned upside down, and try to visualize yourself kind of walking over to that thing and trying to decide, should I walk that way around or should I walk that way around, so that as I walk around upside down, which way has the surface on my left? And it's so confusing, right? So if you want to do that, go ahead, right? But I think much easier instead is to think about swirls, and again, thumb down, nothing to it. Look at my fingers of my right hand while my thumb is down. I see which way the swirl goes on my fingers, right? And so here, at that point, the swirl goes that way. Which, think about how that swirl sort of continues around, how that side swipes up against this piece of boundary. It side swipes that way. Does that make sense? Is everybody happy? So very importantly, it's a side swiping. It's not, sometimes students make the mistake of thinking, okay, I'm just going to put that orientation way over here out in the middle of emptiness and just kind of superimpose that on the boundary. Well, that's not the rule, right? You have to be from where the surface actually is and look at how the swirl side swipes up against there, and that side swiping gives you that. Yeah. Okay. All right. All right. Okay, so we've got all of our conventions made. I'm going to start drawing these diagrams. The diagrams are going to be, I think, a really good tool. It's a great way for you to keep all these ideas organized in your mind. These diagrams are going to grow, by the way. By the time we're done, the R2 diagram and the R3 diagram, between the two of them, are going to take up an entire page of the book. Right? So we're going to be adding more stuff to this based on these sort of starting points. Okay, so we're starting off with, by the way, 3 different contexts. We've got R1. There's calculus in R1. We kind of already know calculus in R1. There's a separate little world, separate conversation that has to be had about what does calculus in R2 look like. It's going to be different. There's going to be a kind of a fundamental theorem of calculus in R2 that we're going to develop. Actually, kind of 2 of them, in a way. And then likewise, R3, another separate context. So here are the ideas that we have. Keep in mind we have various kinds of domains, right? So for example, curves in R2 is one of our kinds of domains. And we've agreed that on curves, vector line integrals of vector fields, that's the kind of evaluation that we're going to consider. Again, arbitrary conventions that are going to, take my word for it, fit together really nicely. We have 2-dimensional regions over which we're going to do double integrals of good old, plain old scalar valued functions, etc. Right? We're going to have points into which we're going to plug into functions to get values. All these other conventions, on intervals we do integrals. On three-dimensional solid regions we do triple integrals of functions, etc., etc. Okay, notice the concept of boundary fits in on these diagrams. The boundary of an interval consists of points, 2 points. The boundary of a curve consists of points. The boundary of a region consists of a curve or possibly multiple curves, etc., etc. The boundary of a region is a surface in R3. All right. And notice, by the way, I've got column headers here. The column header is a reference to the dimension of the kind of domain that we're talking about in that column. So this is column 2 in the sense that we're talking about two-dimensional regions sitting inside of R2. Okay. All right, and notice further, boundary always reduces dimension by exactly 1. Right. Okay, so this is what we got. These are the ideas that we've kind of put together. So again, we're going to be adding to these diagrams as we go along. The diagram is going to serve 2 purposes for us. One I've already mentioned. This is going to be kind of an organized way to collect all the ideas. It's good bookkeeping for ideas. Otherwise, if you have a whole bunch of ideas kind of floating around in your brain in no particular order, it's really hard to kind of sort them out. This will organize all the ideas we're going to talk about. Nice, methodical manner. Right. The other thing is, 2 seconds. The other thing is, we're going to start to notice patterns that are going to be revealing themselves on these diagrams. And when we do something neato here, we're going to say, wow, that's an interesting little pattern. What would happen if I were to apply that same pattern over in this different context? Does everything still work? Does the pattern hold? And, yeah, it's going to hold. Right, yeah, you had a question.
Just why is vector fields but not the scalar surface irregular?
Yeah, so that's one of the things we were talking about last time. It's just an arbitrary convention that I'm making. Now, the reason I'm making that convention is because if you look at the generalized Stokes' theorem, and you ask how does the generalized Stokes' theorem manifest in R2 as applies to curves, it manifests like this. That's what an integral of a differential form looks like in this context. It just is, right? Now, I can't show you what the details of exactly how that works because that's graduate level, hardcore stuff. But that's what it is. Yeah. And sadly, that's going to be my answer to a lot of questions along those lines. Why are we making this choice? Because the generalized Stokes' curl theorem, or the generalized Stokes' theorem, says so. Yeah. All right. Okay. All right. Okay, so moving along, let's start noticing patterns. The first one we're going to see is the fundamental theorem of calculus. We're going to be in this R1 diagram. Right? We're going to look in the R1 diagram, and we're going to. Good news, y'all already know the fundamental theorem of calculus. Right? So I'm going to kind of walk us through a point of view on the fundamental theorem of calculus for the purpose of seeing what the pattern is. How does it look on this diagram? What does that look like? That's going to give us a pattern, and that's a pattern that we're going to continue to try to apply in these other contexts. Okay. By the way, a lot of math gets done like this. We notice something neato, and we say, hey, what's the analogy between this and this other context? And let's see if it works in this other context, and very often it does. Okay. All right, so here we are in the R1 diagram. The starting point of the conversation is going to be that I have a function in column 0, and I have an interval in column 1. Okay, that's my starting point. With that as a given, I'm going to take that interval in column 1. I'm going to look at its boundary. Don't forget the boundary of an interval is 2 points, but don't forget the orientations. Right? We have a positive orientation on the right endpoint, a negative orientation on the left endpoint. Okay. All right, now I notice, hey, I've got a function and some points, and I can plug in a la this pattern, and if I plug these oriented points into this function, I get that as my output. Right? I got f of b and f of a, but wait, it's a negatively oriented a, so I actually get negative f of a, not positive f of a. Everybody on board? You can probably start to see things shaping up already. We all recognize this little formula right here? Right? Okay. All right. So this evaluation here, we think of this as happening in column 0. I guess it kind of did, right? The big idea, and again, the pattern that's going to continue to all the other big theorems we're going to talk about, is we're going to try to see this result as something that, in a way, actually happens in column 1. I would like to see this expression as being an integral of something over the original interval. Now, again, y'all know how this is going to play out, but how would I go about making that connection? Okay. Next big idea. Going to leave this dangling here for a second. Okay. Next big idea. This is a neat fact. This is about how intervals work, but boundaries accumulate. I'm going to say it. Now let me go to this diagram here. Y'all all recognize this picture. If you have an interval from A to B, you can take that interval, you can chop it up into pieces. Again, you've seen that a million times. Okay. All right. I say boundaries accumulate. Let me first talk about what I mean by accumulate. This is one of the features of integrals that we talked about a while ago. Remember, if there's a question that you're dealing with, like let's compute the mass on this interval, or let's compute the amount of area sitting over that interval, or whatever it is that you're going to compute with an integral on that interval, it has to have this feature of accumulation. It has to be true that the expression you're interested in as applies to the whole interval has to equal to that same quantity as applied to individually all the subintervals. And note, this applies to mass. The total mass is indeed that mass plus that mass plus that mass, etc., etc. Okay, so mass accumulates. So the observation I want to make here is that boundaries accumulate. It's kind of a weird way to think about boundaries, but here's the observation. Let's look individually at that one subinterval. Its boundary consists of, well, that as a starting point and that as an ending point. That's the boundary as applies to that first subinterval. Now let me move this out of the way just for cosmetic purposes, but this is a picture of the boundary of that first subinterval. Here's the second subinterval. It has a boundary. Starting point, ending point. Keep in mind, starting points being left endpoints are oriented negatively. The right endpoints are oriented positively. Okay. So again, let me move this out of the way. The third interval is going to be something like that. It has a starting point, it has an ending point, negative orientation, positive orientation. And let's get this over here out of the way. And et cetera, et cetera. Right? The last one, just for the last couple here, I guess I'll do. So starting point, ending point. Let's get this out of the way. And the last subinterval, starting point, negatively oriented, ending point, positively oriented, and let's get this over here out of the way. Okay, now what happens when you start adding up these boundaries? Now keep in mind, the outrageous assertion that I'm making is that boundaries accumulate. All right, so the suggestion would have seemed to be that if I were to add up all these boundaries, I would get that I would get the boundary of this whole thing? Well, the boundary of that whole thing has but a single starting point and a single ending point. Now, how could all of this boundary nonsense in here add up to the exact same as this boundary here? And it works just fine, actually, because think about what happens when you start adding up all these little boundary points. X1 appears twice, but with opposite orientations. We have a positively oriented X1 right there, but we have a negatively oriented X1 right there. And when you add a positively oriented and a negatively oriented together, they just disappear in a puff of smoke. Gone. Right? Likewise, X2 disappears in a puff of smoke, etc. All of these, what you might call interior boundary points, right? They all just cancel all the way down to xn minus 1. They all just disappear in a huge cancellation, and all you're left with is that one starting point that doesn't have anything to cancel with, and this one ending point that doesn't have anything to cancel with. Right, now algebraically, that looks like this. Here I'm adding up all of the boundaries, starting point, ending point, starting point, ending point, etc. And when you move parentheses around, notice X1 appears twice, but with opposite orientations, and therefore it cancels, and everything in here cancels except for, after all the cancellation is all said and done, all you're left with is that starting point A, negatively oriented, this ending point Xn, positively oriented. The algebraic version of the same thing that we just saw visually up here. All right, now so this is a creepy way to think about boundaries, but very important as it's going to turn out. Mass accumulates. We can see mass accumulating. It's a physical quantity, for crying out loud. Of course it accumulates. Ants accumulate. If we were looking at the number of ants walking around on here, ants accumulate, right? Boundary is a geometric concept. It's worse than that. It's an abstract geometric concept with, negatively oriented points. It's a weird concept, but this new concept we've created, geometric and abstract though it is, has the same feature of accumulation that lots of other things that we've studied have. Okay, so that's going to be a kind of a big deal. And plug all this into some function. This function that we have here, keep in mind that's what we're doing. We're taking this boundary, we're plugging it into the function. Plug that into the function, and plugging in the boundaries of the individual pieces gives you that. Plugging in the boundary of the union gives you that. And again, lots of cancellation. That's going to cancel with the first term inside of the next term, etc. So that there's a cancellation there. Lots of other cancellation. This is going to cancel with the one before it, and all you're going to be left with is those two terms right there. Okay. All right. Yeah. Okay. So this I'm going to take a slightly different point of view on. This is a more algebraic statement. It's not so much geometric. It's more algebraic, right? But let's look at this thing here. This I can think of as a new type of quantity. This isn't a boundary. This is a boundary that's been plugged into a function. But I appeal to your previous experience. This represents something we've talked about before. That is change. How much did f change over an interval? So this equation here you could view as saying change accumulates. The total change in a function is the sum of, how much did it change on the first subinterval plus how much did it change on the second subinterval and the third subinterval, and keep adding up the little micro changes down to the change on the last subinterval, and the total of those changes is the overall change. So now again, pretty relatable. Change accumulates. It's another non-physical thing that we're thinking of as having this kind of physical property. Okay. All right, so that context set. Let's start writing stuff down. We're almost done with the fundamental theorem, by the way. But change accumulates. It's a consequence of the fact that boundaries accumulate. I can take a limit as n goes to infinity, and it doesn't matter because this, while it has an n in it, and you would think that this depends on n, no matter what n is, you always get the same thing. So we're taking a limit here as n goes to infinity of something that's always the same value. So you can take a limit for free. We're taking a limit of a constant. This is starting to look a lot like a Riemann sum, kind of. We're missing the delta x over here. I'm going to give myself a delta x by doing this little algebraic move where I multiply and divide by the same thing. Right? Now this is really looking like a Riemann sum. I mean, really looking like a Riemann sum, right? I'm going to rewrite this numerator here as delta f. Change in f, again, that's what that is. That numerator is the change in f. So let's just give it that familiar name. And here you go. F of b minus f of a is this Riemann sum. That Riemann sum is a very familiar integral. I am sweeping a little formality under the rug. It's easily fixed. I just don't want to draw focus away from the big points here. But technically moving the limit inside of the summation is a thing. It's not our problem. This is, of course, the derivative, and there's our fundamental theorem of calculus that y'all all recognize. Okay, now a reminder: why did we do this? What was the purpose of this discussion? I am not trying to persuade you that the fundamental theorem of calculus is true. I know you already know it, and know you already believe it, and you've probably seen an easier proof than this, which is good. The purpose of this conversation, again, is to set a framework. And so let me remind you what the framework is. We started with, in the R1 context, we started with a function there and a domain there. We took the boundary. We plugged in. And we found a way to view this as actually accumulating over the original interval by seeing explicitly how that expression accumulates over the interior. Okay. All right. How are we doing? Is everybody on board? All right. This pattern's going to hold. All right. Okay. So let's say. So right to kind of spike the football on this. Here was our original diagram. We had, these notions here and these notions, conventions, you might say. We talked about the notion of boundary. All of that is there. What's new is we have a theorem, right, that says that if you take a boundary of an interval and the derivative of the function, then these resulting evaluations are equal. That's our new theorem. Again, notice the pattern here. That pattern is going to be reappearing a lot as we go through the rest of this chapter. We also then have a new object up here in our kind of top part of our diagram. The derivative is the thing that you do to kind of complement, if you will, the action of the boundary. You might say that the derivative is the complementary operator to the boundary operator. That's one way to think about it. Okay. All right, but now we have an appended diagram, and let's move along to the next section. So what I'm going to try to do here now, in 2 dimensions, you'll notice, we're going to see our first 2-dimensional theorem, 2-dimensional boundary theorem. And I'm going to get to it by ripping off the pattern of what we just saw, right? So we're gonna say, okay, well, looking back at this diagram, we took one of these and we did that, and then we plugged into there, and we got some expression, and then we asked if I could make it add up, kind of like that does. Even though the context is going to change, I'm going to just kind of blindly hope that maybe if we follow that pattern, maybe everything will fall into place. In this now two-dimensional context. And here we go. I have a function in column 0. I have a domain in column 1. Now let's think about this, though. This is no longer in R1. We're now in R2. So this is no longer an interval. Our diagram says that you should look at curves in space. Okay, if you insist, diagram. Okay, so let's see what happens if we do that. Now again, following the pattern, we took the boundary and then evaluated and got some expression, and then we asked if I could rewrite it like so. So, okay, here we go. I'm going to take the boundary of this curve and plug it into this function and see what I get. Okay, well, our curve has a boundary that consists of negatively oriented A, positively oriented B. And I'm going to plug that in and get, again, f of B minus f of A. No surprise. Okay. All right. Again, I claim that boundaries accumulate. Algebraically, here's how we write that down. The boundary of the original curve is the sum of the boundaries of the subcurves. Now, new geometric context. This is geometrically now not the same fact. We need to reconsider. Wait a second. Just because we're trying to follow a pattern doesn't mean it's true. We need to reconsider, is this true? Is the boundary of the original actually the sum of the boundaries of the individual pieces? Okay, let's draw the picture. Here we are. The first piece of curve, negatively oriented, positively oriented. Let's get this over here out of our way. Second piece of curve. Let's see here, negatively oriented, positively oriented. Let's get this over here out of our way. Next piece of curve. Y'all can probably see the pattern. This is going to otherwise take a long time, but negatively oriented, positively oriented. Let's get this little thing out of the way. So let me say here then, etc. as you go around. And you can see the cancellation happening in, a slightly different way, but morally equivalent. That point, whatever that endpoint is, that's the, between the first subcurve and the second subcurve, that appears twice with opposite orientations, and then in the summation cancels. Right? The next one here, that point, that next sort of point between the subcurves, that point appears twice with opposite orientations, and in the summation cancels. Etc., etc. That's going to cancel, that's going to cancel, etc., all the way down to near the very end, and the only points that aren't going to cancel are that starting point, negatively oriented, that ending point, positively oriented. Namely, you're going to get the boundary of the original total curve. Yeah? Does everybody see how this is morally identical to what we did in the fundamental theorem of calculus context? Okay. So, by the way, here's the algebraic version of that. It's the same thing. In fact, this is another one of these cases where when I was writing this thing in the book, I literally just copy-pasted from the previous section and then went in and made the appropriate little tweaks with the little vector arrows and everything. But it's the same morally. Okay. All right, plug it into a function. We get this, again, familiar result that change accumulates. The total change in some function f, right, is the sum of a bunch of individual changes that happen over the subcurves, right? So the total change is the sum of the little bits of change. Change accumulates. Again, pretty believable. Let me give you a physical sort of version of this, something to think about, right? Just kind of just to give you satisfaction, physical satisfaction. Let's suppose as we were driving along here on this curve, suppose we're keeping track of our altitude change, right? Maybe this is a road, right? And I'm going to start at that point on the road, and I'm going to end at that point on the road. Well, I hope it comes as no surprise. But if you keep track of how much did your altitude change on that first little piece of road, and then add how much did your altitude change on the second piece of road, and then add how much did your altitude change on the third piece of road. If you add up all the individual changes in altitude as you go along, it's no surprise that you get the total change in altitude over the whole curve. Highly, highly believable. Okay, so here we go. Change accumulates. Total change is the sum of all the individual changes in this function that we're keeping track of, altitude or whatever. Let me rewrite this as change. And now I'm going to flash you back to chapter 4, change in f, change in the output value of the function. Let me actually go back up here to our diagram. Keep in mind we're looking at the domain here. The values of the function f are over here in some target space. Call that the z-axis. And output changes, how much the function changes over some subinterval, delta f, relates to the input change, right, on that subcurve. Input change and output change are related by the derivative. And, appropriate to the context, in this case, we're talking about a change, a vector change in the domain in space, right? And this is a real valued function. And so the nature of the derivative that connects that input change to that output change is dot product with a gradient vector. Right? So, here you go. Dot product with the gradient vector turns this input change into this output change. Yeah, is everybody on board? Okay. A little bit of a twist. We didn't do it quite exactly like this when we were talking about fundamental theorem of calculus, but context is different. So, okay. All right. And oh my gosh, check it out. That looks exactly like a vector line integral, right? It just is. This is the definition of a vector line integral. Right, dot delta x vector, right, limit of a summation. So it is straight up a vector line integral. My integrand is the gradient of the original function f. And we have ourselves a brand new theorem inspired by the pattern that we sort of noticed with the fundamental theorem of calculus, blindly and optimistically applying that pattern in this totally different context of a curve floating around in space, and yet we get a very analogous result, very recognizable result. Everybody on board? Okay. All right. So theorem. If you have a function, it needs to be continuously differentiable. That's whatever. The line integral of the gradient of that function is the total change in the value of that function. Or said differently, if you find yourself wanting to compute a line integral, here's a magic formula that will compute it for you. And now, just before we put the finishing touches on, let's notice the potential applications of this. How did we used to compute line integrals? We used to compute line integrals, I had to parameterize the curve, and I had to do the whole, vector field dot x prime, and do an integral dt, and then I had to actually do the integral. This is saying, nah, just plug into that formula. That's awesome. Is everybody on board? Okay. All right. Okay, so finishing touches. Here's kind of a summary of what we did. We started with a function and a curve. We took the boundary of the curve. We evaluated to get this expression. We asked if we could find some way to get this expression to be viewed as, an integral, vector line integral over that curve. Does it accumulate over the curve? And if so, in what way? And we found that this is the formula for it. Right. Furthermore, notice we have a new object. The integrand there tells you what should you do to your function to get the new integrand. And it's the gradient operator. So we have our new, I'm going to append the diagram like this. Here is our original R2 diagram. We had all of these objects. We had that too. Right. We had this idea of a boundary. And we have now developed that the gradient operator is sorta complementary to the boundary operator. Namely, applying the gradient operator just after you apply a boundary operator. What that does is that gives you a theorem here that says that this evaluation and this evaluation are the same. And notice the little diagram chase that I just did there, right? The pattern of how these arrows look, that's exactly the same pattern that we saw with the fundamental theorem of calculus. Okay. All right. Okay, so got ourselves a new theorem. Let's dust it off and use it. Let's see what we can do. I want to compute this line integral. Here's the vector field. Vector field is given there. The curve over which I want to compute its vector line integral is the counterclockwise oriented upper unit semicircle. So that's a curve. We got a curve. We got a vector field. How do we compute the line integral? Well, look, you can totally chapter 5 this problem. Right? Parameterize the curve. It's a semicircle. It's easy to parameterize. Not a big deal. Instead, though, let's notice the following. This vector field here, that vector field is a gradient. Now, how do I know that this vector field is a gradient, thus allowing me to use this theorem? Just observation. Okay, I'm just going to just notice that, hey, check it out. This function, that function there, little f, if you take its gradient, sure enough, you get capital F. Just check it out. Right? Everybody see what happened there? Now, you should be a little uncomfortable with this, pulling a rabbit out of a hat like that. You should be worried about the possibility. Am I going to be expected to just pull rabbits out of a hat? Like, where did this function come from, and how am I going to find it in my life? Right? And that's a legitimate concern. We'll get to that in a few minutes. Right now, I want to focus on how powerful the theorem is and how convenient it is to use it. So I'll show you where that rabbit came from momentarily. For the moment, let's just observe that, wow, look at this. In fact, this is a function whose gradient is that vector. This vector field is a gradient. Being as it is a gradient, I'm not just asking, in this original question, I'm not just asking to compute a vector line integral of some vector field, random vector field off the street. It's a special vector field. It's a vector field which is a gradient, and we have this powerful theorem for computing vector line integrals of gradients. Yep?
So is it the gradient of the integrand then? Or
I'm sorry?
Is it the gradient of the integrand? Does it have the integrand in that case?
You said it. What it are you talking about?
Is F the integrand?
this vector field is the integrand. Let me just stick with green. This vector field right there is the integrand.
Where does lowercase f?
Lowercase f is the function there whose gradient is the vector field f, capital F. So there's sort of two separate algebraic objects running around here, right? There's the original vector field, and then there's the scalar valued function whose gradient is that vector field. Let me go up to the diagram. We are given a vector field, and we have just found a scalar valued function whose gradient is that vector field. Yeah. Yep. Right. Okay, so what does the theorem say? The theorem here then says that, if you want to compute a vector line integral, cool, f of b minus f of a, you just have to make sure to have found that function, f, that function whose gradient is the original vector field. By the way, I hope you would go along with me if I were to refer to this vector field, this function, the function whose gradient is the thing I'm given. How about we call that the anti-gradient? Kind of along the lines of antiderivative, ripping off the terminology. Right? I'm going to call this an anti-gradient. Okay. All right. So f of b minus f of a with the anti-gradient computes the line integral, and that's a really easy calculation here. So the theorem, there's the fundamental theorem of line integrals. The anti-gradient function is what I plug those endpoints into. By the way, you do have to think through the curve, right? Let's look at our curve for a moment. Our curve is the upper unit semicircle with counterclockwise orientation. Okay, here's the unit semicircle. The upper unit semicircle. This is the unit circle. The upper unit semicircle is that. Counterclockwise orientation means oriented that way. Now, I don't have to parameterize it. That's the whole beauty of this theorem. I don't have to parameterize and plug and chug. But I do need to be able to see the orientation, because I have to be able to deduce from the picture and from thinking about the orientation which point is the starting point and which point is the ending point. Right? And you see there that our starting point is 1, 0, and our ending point is negative 1, 0. So we have a negatively oriented 1, 0. We have a positively oriented negative 1, 0. And you can see that in the formula right here. We have the positively oriented negative 1, 0 and negatively oriented 1, 0. Yeah? Pretty good. F of b minus f of a, if you prefer, and it's, b is the end point, a is the starting point. Okay. And then a little arithmetic, and boom, there we go. Problem solved. Yeah.
Is the unit semicircle considered a closed region?
No. So there's a little bit of terminology here. Let's talk about that, just as a reminder. Circle is a curve. Disk is a solid region. Right, so the word circle just means curve. There is no region. There's no two-dimensional region to talk about when you say circle, right? So then if you say semicircle, that literally means just half of the circle. Semicircle is just half of the circle. And, there's this temptation that students have, and I get it, right? I totally get it. But let's take a moment to dwell on the sloppiness here. This urge that students have to fill that in, right, comes from sort of on some level kind of thinking that we're actually talking about that somehow or something, and oh wait, but it's got to be a curve, oh I guess I'll take the boundary of it or something, right? But that's just not what it is. The circle is this, and so the semicircle is just half of that. Is that good for everybody? Lots of students get stuck on this point, so make sure to be careful with the terminology. Yeah. Okay, great question. Anybody else? How we doing? Yeah. Okay, right. So we just computed ourselves a vector line integral. We didn't parameterize anything. And I didn't have to look at a resulting function of t and then integrate some function of t. I just make a casual observation about, oh, look, that's an antigradient, and then bam, done. Okay. All right. I hope it comes as no surprise. There is a highly analogous theorem in R3. It looks exactly the same. The only difference is that here we're doing an integral over a curve in 3 dimensions instead of 2. But it's still gradients and antigradients, and f of b minus f of a. Morally same theorem. If you'd like to see an argument for how to justify it in 3 dimensions, geometrically, the argument changes like this. We just add a third axis there. Now we have a curve in 3 dimensions. Right? And you can see it's all the same pictures are going to apply, just view it as being in 3 dimensions. I mean, it's really no different. Right? So y'all could reproduce all the exact same arguments, and of course, no surprise, you come to the same conclusion. Okay. All right. So here's an example in 3 dimensions now. Oh, by the way, notice our original diagram in R3 was this. There's our R3 diagram. And we have a new gradient operator in that R3 diagram sitting. That is the operator that's kind of complementary to the boundary operator. Right? And I should put that in green, our old boundary operator. And we have our new theorem, our fundamental theorem of line integrals. Looks exactly the same. Of course it is. Okay. All right, yeah, so let's apply this now, and pretty straightforward. Suppose I want to compute a line integral. I am given a vector field, and I am given a curve. Now this time, the curve is parametrized for us. We're not given a geometric description of this curve. We're given a parameterization. We want to compute a line integral. There is a temptation, and you gotta kind of stop yourself on this. There's a temptation to look and say, "Oh, well, it was given to us parameterized." It's like they're pushing me in the direction of plugging in the parameterization and doing the chapter 5, pull back f dot x prime dt and all that business. Really looks like you ought to do that. And you can, and under some circumstances it might even be a good choice. But let's see if we can instead do this with fundamental theorem of line integrals. By the way, look how ugly this would be. If we did this the chapter 5 way, my x and my y and my z are not nice. And I'm going to be looking at x prime dot the vector field. The vector field has x's, y's, and z's in it. I remind you, our x's, y's, and z's are not nice, right? So f dot x prime is not going to be a pretty picture. Now, you can do that if you want, right? But it's going to be a bummer. Okay. So the much better way to do this problem is to look at the vector field, and again, notice that this vector field we're given is a gradient. It is a gradient of a function that I can see right there. If you don't believe me, check it out, right? Take that function I just circled in blue and take its gradient. You get that? Yeah? Again, I pulled a rabbit out of a hat. Where does the rabbit come from? We'll talk about how to get your own rabbit in a couple of minutes here. But that detail aside, having found an anti-gradient, we are now armed to apply the fundamental theorem of line integrals. Fundamental theorem of line integrals says that as long as your integrand is a gradient, you can compute it by plugging in to the anti-gradient, like so. What endpoints do you plug in? Well, okay, the endpoints, you got to look at the starting value of t, plug that in. That gives you your starting point. Right, you got to look at the ending value of t here, plug that in. That gives you your ending point. Right, so that's f of b minus f of a. B and a comes straight out of the parameterization and arithmetic. And there's your answer. How we doing? Everybody happy? Doesn't that beat the chapter 5 approach where we'd have this great big nasty integral involving exponentials and cosines and fifth powers, for crying out loud, right? That would be a nasty integral. Is everybody happy? Okay. All right, so let's talk about how to find those anti-gradients. How do we pull these rabbits out of hats? This is a pretty straightforward observation. It's just a matter of kind of breaking it down into components. No big deal ultimately, but saying that we want to find a function f. A function f whose gradient is a given vector field PQR. Right, so PQR is given. And I want to kind of reverse engineer, find that f such that when I take its gradient, I get f, capital F. Okay. So that's all I've got written down here, and I just need to solve for f, namely this f in each of these equations. So I need to solve for f in each of these three equations. And another way to say that is I need to take three anti-partial derivatives. I mean, these are three partial derivatives. Solving for f in each one means take an anti-partial derivative. I'm going to denote the anti-partial derivatives in the way you would expect. Right? And you've got three formulas for finding f. Now, this is a bad news, good news situation. It is not the case that you can just pick any one of these formulas and that'll tell you your f. That's the deceptive sort of seeming. Looks like it'd be good news. It's not. You have to do all three of these. Because all three of these formulas have to be true. Because all three of these equations have to be true. Because I need my function to have all three correct components functions in order for this to actually be true. Right? And so you might say, well, but if I find this, doesn't that tell me what this has to be? Temptation? And no, it doesn't. Here's the really bad news. Sometimes this f that we're looking for does not exist. In fact, often this f that we're looking for does not exist. There is no anti-gradient. This is where the analogy between single variable calculus and multivariable calculus breaks down. One of the ways. In single variable calculus, every continuous function has an antiderivative. I mean, sometimes they're hard to find. Sometimes I can't even write down what the antiderivative is. But they're always there. Right? Not so in multivariable calculus. Sometimes the antigradient doesn't exist. And the way that's going to manifest is, again, you got to calculate all three of these things, and they better all be equal. If they are not all equal, then you are looking for something that's not there. There is nothing that satisfies all three of these equations, and then there is no antigradient. Okay, so that's the bad news. There's another detail we need to talk about before we start cranking. And that is, let's talk about these constants. When you take an antiderivative, you always say plus c. Reminder, why do we say plus c? Well, we say plus c because when we take a derivative of both sides, if I take a derivative of both sides of this, then that turns into that, and that turns into this, and this thing turns into 0. Right? So, constants, when you take the derivative, you get 0. So you kind of have to add in these constants because, well, it wouldn't, any constant you put there would not contradict the equation we're actually interested in. Yeah. Okay. Here's the thing. These are partial derivatives. So what I'm interested in then is not actual constants. I'm simply interested in things that when you take their partial derivative, give you 0. And if I'm taking an x partial, any function of y and z has x partial equal to 0. Yeah? Alright, so this is, again, kind of a bad news, good news thing. This idea of a constant, this is what you might call, by the way, a partial constant. Because it's constant with respect to a partial derivative. Okay, so the problem just got a little bit harder. Not only do I have to compute these anti-partials, but I also have to throw in the ambiguity of these unknown partial constant functions, and I got to see if these things are equal. Now that's the bad news. Here's the good news. These partial constants, these are actually flexibility for you to try to find an actual function f that does indeed satisfy all these equations. You get to pick what these partial constant functions are, kind of. Right? So it's not bad news. It's good news. That's your freedom. That's how you can make it all sort of come together. So let's see how this works in practice. Here is a vector field. I want to compute the anti-gradient of this vector field with these 3 components. All right. So those 3 components, those are the things I need to take the anti-partials of. Right? I've got to take the x anti-partial of the first component, the y anti-partial of the second component, the z anti-partial of the third component. And of course I've got these constant, partial constant unknown functions over here to play with. Okay. Easy anti-partials. Now make sure you can do all the antiderivative stuff. Partial antiderivative, it's just like partial derivatives, just backwards. Right? So think that through. Hope you get this. Are these 3 things all equal to each other? No, they're not. Right? And there's a temptation to throw up our hands and say, well, too bad. Right? These 3 things had to be equal, but no. It's not those 3 things. It's these 3 things that had to be equal. I have this flexibility of choosing whatever partial constants I want appropriate to the component. And that's what I have to make all equal to each other. So I get to start playing a game now, which is what would I like for these things to be in my attempt to make these 3 things all equal to each other. Everybody see the game? All right, so here's kind of how I like to play the game. I see that there's an x squared y there, and I see that there's an x squared y there. So I kind of feel like the right answer is going to have x squared y in it. And I don't see x squared y in here. So I'm going to just set this thing equal to x squared y. And now I'm happy. Right? So those terms all check out at this point. Okay, continuing. I see an xz cubed there. I see an xz cubed there. I don't see an xz cubed in here. That's bad. Oh, well, I could just make this xz cubed. Yeah? Okay. Lastly, I see 2yz there, I see 2yz there, I don't see 2yz there. That's a problem, but it's easily resolved. I just make this 2yz. And now check it out. All of these expressions are actually equal. That and that and that all have the exact same three terms. The purple one, the green one, the orange one. And so this thing, that thing, that's my F. That's my anti-gradient. Yeah? Everybody see the process? Okay. All right. Sometimes you cannot win this game. Again, sometimes the anti-gradient's just not there. It's just there is no anti-gradient. And here's an example real quick. Let's see how we're doing on time, by the way. Oh, no, we were out of time. Okay, so anyway, I'll show you an example next time of a vector field that does not have an anti-gradient. All right, see y'all later. Have a good one. Oh, and by the way, I'm going to go ahead and declare us finished with this section. That last example that I'm going to show you tomorrow is not essential for this section. It's just kind of cultural. So we are done with section 6.2. Okay. See you later.